Okay, guys, I'm going to be talking about stoichiometry with solutions. So, using precipitation reactions, but doing the stoichiometry math behind those reactions. Okay, so this is on the back of the net ionic PL. This itself is not PL. This is like notes or practice to see how to work out these problems. Okay, so we're going to start with question 1, which asks what mass of precipitate is formed when 71.3 milliliters of a zero point 0.5 molar iron 3 nitrate solution is mixed with 112 milliliters of a zero point 0.8 molar sodium carbonate solution. So to do any stoichiometry, the first thing we always need is a balanced equation, okay? And so in this scenario, I am taking iron 3 nitrate, which is FeNO3, crossing my charge down, 3. And that is going to be mixing with sodium carbonate, which is Na2CO3, coming down from that carbonate. And what that's going to form is iron 3 carbonate. That's my solid precipitate. And some sodium nitrate. So to balance this equation, I need 2, 3, and 6 of those. Okay. So now that I have my balanced equation, we're going to have to find the moles. But the way we find moles in a solution scenario is different because I don't have any mass, I don't have volumes of gases, I don't have molecules, right? I'm given a volume and a concentration. And so you have to remember that molarity is moles per liter, okay? So any molarity times a volume is going to give me my moles. However, it's moles per liter, and so I need my volumes to be in liters, right? So I'm going to take my milliliters and move my decimal place back, so that's 0.0713 liters. If I want to find the moles, that's going to be equal to its molarity, which is 0.5 moles. Okay? So all I have to do is multiply my volume by my number of my molarity to get my moles. And so here, X is going to equal 0.0357 moles. That's of the iron 3 nitrate solution, okay? So I wrote that underneath that one so that we would remember where that goes, right? I'm going to do the same thing with the sodium carbonate, right? So I'm given a 0.8 molar solution. I want to know the moles. But again, I need that volume in liters. So when I multiply these two together, that solves for X. 0.8 times 0.112. That's going to be 0.0896 moles. And that's going to be of the sodium carbonate. I'm going to write that there. This is of the iron 3 nitrate. Now that I have moles, now I can do stoichiometry, and I want the mass of precipitate. So I know that the sodium nitrate, that's aqueous. That's not my precipitate, right? I want the mass of the iron 3 carbonate. And so 2 givens, right, each of my reactions, 2 T-charts, 2 answers, like any limiting reactant problem, and then we're going to pick the smaller answer. So here, they're in a 2 to 1 mole ratio of the iron 3 nitrate to the iron 3 carbonate, and every mole of iron 3 carbonate is going to weigh a lot, right? So Fe weighs 55.8, times 2 plus 12 times 3 plus 16 times 3 times 3, 291.69 grams. And kind of wrote over my S there, I'm sorry. So then my T-chart, I'm going to take my small amount of moles, and this would make 5.21 grams of Fe2CO3. But I don't know if that's my correct answer. So I'm going to write the same T-chart again, but this time using the sodium carbonate. Okay. So with the sodium carbonate, they are in a 3:1 mole ratio of sodium carbonate to the iron 3 carbonate. And every mole weighs 291.69 grams. So 291.69. I'm going to double check that. 0.0896 divided by 3 times 291.69 is 8.71 grams of Fe2CO3. So I can't make that much. It's too much. Right? And my correct answer is going to be my 5.21 grams of FeCO3. Okay. Let's do another one because that was so much fun. So in question 2, right, it says when you use 25 milliliters of a 0.4 molar HCl to produce hydrogen gas, how many grams of zinc does it react with? They give me a balanced equation. Okay. Not exactly precipitation, but it's still a net ionic. Okay. So then I've got 25 milliliters of a 0.4 molar HCl. So that's where my moles are going to come from. Okay. And once I find the moles of this, I can find the grams of zinc. So pretty simple on this one. So 4 molar is a number of moles of HCl over this total volume in liters. Right, so I move my decimal place over 3 times. I don't want milliliters, I want liters. So I'm going to multiply these two together. 4 times 0.025 is 0.01. It's 0.1. And that's of the hydrochloric acid solution. Two to 1 mole ratio of hydrochloric acid to the zinc that I want to find. So for every 2 moles of HCl, I need 1 mole of zinc to react with it, and every mole of zinc weighs 65.38 grams from the periodic table. So 0.1 divided by 2 times 65.38, I need 3.27 grams. I guess just 2 sig figs. Let's go 3.3 grams. Okay. Number 3, right, is a little bit more involved. Pull that up so you can see it. Number 3 says throwing some scrap iron into gold nitrate solution causes the gold metal to precipitate. What volume of a 0.5 molar gold nitrate solution would react with 224 grams of iron metal? Oh, okay. So for this one, we're given the mass of iron, right? We're given that we have 224 grams of iron. And we know the concentration of this gold nitrate, but what we need to find is the volume. And we're going to need to use the 0.5 molar solution to do that, okay? So first, to do anything with molarity, I need moles, right? But I need moles of the solution, not moles of the iron. So I'm going to start with stoichiometry. 224 grams of iron needs to get converted. Iron weighs 55.85 grams in 1 mole of iron. And iron is in a 3 to 2 mole ratio. To the gold nitrate solution that I need. Okay. But I don't want mass of this, right? I want the volume in that solution. So I'm going to stop here. 224 divided by 55.85 times 2 divided by 3. That equals 2.67 moles of the gold nitrate solution. If those are my moles, what volume would make a 0.50 molar solution? Right, so we just need to solve for x here. I'm going to multiply by x on both sides. And I'm just going to use this as my space, right? 0.5x. And so I'm going to divide by 0.5 on both sides. So that I would need 5.35 liters of that half a molar solution of gold nitrate to react with the iron metal. Okay. Number 4 has an ABC, which means get excited. Here we go. It's just breaking it apart. So it says when a solution of lead 2 nitrate and aluminum chloride are mixed, a precipitate forms. Write the balanced formula for the equation for the reaction. So the formula equation is our molecular equation. So lead 2 nitrate is lead crossed down the 2, and aluminum chloride, I had to cross down the 3. That's going to make lead chloride and aluminum nitrate when I switch my partners and recross my charges. Then to balance this equation, I need 2 and a 3 and a 3 and a 2. So then B asks, what volume of a 0.2 molar lead 2 nitrate solution, so that's like finding the volume that we did in number 3, is needed to form a precipitate when added to 2.48 milliliters of a 0.3 molar aluminum chloride solution. So because I know both of these things, that's where I'm going to start to get my moles. Right, so 0.3 molar is some number of moles over my volume, which is not very big, right? Because milliliters to liters is 0.00248. And so this is going to give me a small number, 0.000744 moles of aluminum chloride. Aluminum chloride is in a 2 to 3 mole ratio with the lead nitrate. So I do my stoichiometry to get my moles of lead 2 nitrate. But the question wanted volume knowing the molarity, right? So that's going back to what we did before. If I know my moles, 0.0112 moles over some unknown volume is in a 0.2 molar solution, what is that volume? And so that X volume would be 0.00558 liters, which is 5.58 milliliters. That's how much I would need to react with the 2.48 milliliters of the aluminum chloride. Okay, so then C says what mass of precipitate formed in B. Here you can take any set of moles that you would like, but you need to know which one's the precipitate. So the precipitate is the solid one, and that's going to be the lead 2 chloride. The aluminum nitrate on your solubility rules is still aqueous in solution, so it's not the solid precipitate. So to find the lead 2 chloride, it's in the same mole ratio as the lead nitrate, and I already know my moles of lead nitrate from B, so I'm just going to use that 0.00112 moles. They're in the same mole ratio, so this is the moles of the PbCl2, and all I have to do is multiply by its molar mass. Lead weighs 207, and then 2 chlorines is 71, so 278 will be my molar mass. And so that would make 0.311 grams of lead 2 chloride. Okay. Then one last question and we'll be done. Number 5 says how many milliliters of a 2.5 molar nitric acid solution that contains enough nitric acid to dissolve an old copper penny that has a mass of 3.94 grams. So I know that I have 3.94 grams of that copper. I know the concentration of my nitric acid solution, and again, I'm trying to find that volume. I'm going to find it in liters and then have to convert it to milliliters. Okay, so that's my plan of attack. So if I start with my given that I can do stoichiometry with, grams of copper weighs 63.55 grams in 1 mole of copper. And they are in a 3 to 8 mole ratio to moles of HNO3. So I want to stop here, right? 3.94 divided by 63.55 times 8 divided by 3 is 0.165 moles. I don't know the volume, but it's in a 2.5 molar solution. What volume of that do I need? So I'll multiply by X and then divide over. So moles divided by molarity is going to give me 0.661 liters. No, 0.06, sorry. 1 liters. And so moving my decimal place back, 1, 2, 3, that is 66.1 milliliters. That's the volume of the nitric acid I need to dissolve an entire penny. It has to be an old penny, otherwise it's not pure copper. You'd also have zinc involved. Okay. Super fun. Have fun doing yours.